So now let's kind of imagine where life could be in our solar system and go look for it, see if it's there. So the closest and easiest place to check would be Mars, because we know Mars used to have a thicker atmosphere. Mars used to have a magnetic field, and Mars has evidence of having liquid water in the past. So maybe in the past, Mars might have had single cell organisms living on it. You're only going to find out if they're there by going and looking at them. So we've got rovers on the surface, most notably right now Curiosity. It's going around taking samples. It has a lot of scientific instruments to see if there's any evidence of life. We haven't found any yet. Another place we should look is Jupiter's moon, Europa. Europa is the Jovian moon that we think has a lot of tidal heating from Jupiter, and its crust is water ice. We can tell that from spectra. And because of Europa's magnetic field, we think that it has a liquid ocean underneath that frozen crust, and the internal heat is coming from tidal heating. And we'd have to get a probe out there, and it'd have to melt its way through the crust and then swim around in the ocean, taking samples. The other two moons, Ganymede and Callisto, also show some evidence of having subsurface oceans, but Europa is definitely the strongest bet. The energy for life on these moons would not come from sunlight. It's much further away from the sun than it is from Earth, but there would be energy by the volcanic vents. If we branch out a little bit and maybe try to imagine life that can live without liquid water, you might be able to argue that life might be able to find a way to survive on Titan. I might imagine kind of a single-celled organism, but instead of being water-based, maybe it would use ethane or methane, because those are the chemicals that are liquid and plentiful on the surface of Titan. This is Enceladus. It has an icy surface. Also, we've seen venting coming from the surface, and it implies that there is liquid water under the surface. It leaves open the slight possibility of life. So to recap, we have found zero evidence of life on any other planet or moon in our solar system. Alright, now in this section we're going to talk about trying to find planets around other stars, so extrasolar planets. And in chapter 10 we talked about how they're discovered and how many we've found so far, which is thousands. And we know several of them are in the habitable zone of their star. But I'd like to reiterate, that doesn't mean that they're habitable. It doesn't mean that they have an atmosphere. It doesn't even mean that they have liquid water. It just means that they're the right distance from their star to possibly have liquid water. So here's our sun, and if you're too close to our sun, it's too hot, there's really no possibility of having liquid water. And of course, if you get too far away from the sun, it's going to be too cold to have liquid water. So Mars is technically in the habitable zone for our star, but because it has very little atmosphere, it can't hold on to the heat, it can't keep a stable greenhouse cycle going on, so it's not actually habitable even though it's in the habitable zone. Now, if you pick a sun that is lower mass than our star, it does mean that the habitable zone moves inwards, because a lower mass star is less luminous, less powerful. So you have to move closer to the star in order to get enough luminosity or brightness to keep your planet warm. One good thing though about being a planet around a lower mass star is lower mass stars can last a lot longer. Our sun can last for about 10 billion years. Some of the smallest stars should be able to last for 100 billion years before they run out of hydrogen. Now, if you had a star that was more massive than our sun, you could reverse these trends. Right? The habitable zone would move further away from the star, but the downside is that star would not stay stable as long. It might only be stable for 5 billion years, or even less. And it turns out that in the galaxy, these tiny low-mass stars are the most common. So if we are going to find aliens, it's probably going to be around a low-mass star. Those stars last a long time. There's plenty of time for life to develop. and there are oodles and oodles and oodles of low-mass stars in the galaxy. This idea is a little bit more questionable, the galactic habitable zone. So it's kind of the idea is that some of the parts of the galaxy are not ideal. So our galaxy is a spiral galaxy, so we've got this kind of flat record shape to it with a spiral pattern. And the most crowded region of stars is in the center, and so the stars are a lot closer. They might interact with each other more, and there's also more supernova down in here, and supernova are powerful enough that they can destroy a planet's atmosphere. And if you go too far on the outskirts of the galaxy, there's not enough nebulas and gas and star formation. And that's important because when our sun and our solar system formed, we had to form with some carbon and with some iron. But carbon and iron, and really pretty much all the elements except for hydrogen and helium, are made by other stars dying, and then that material gets mixed back into the galaxy. So way out here, you're not going to have near as many stars going supernova, exploding, and littering the galaxy with carbon and iron and oxygen and gold and uranium. So it's going to be a lot harder to form solar systems or planets out here. One reason why we think Earth is habitable is because our solar system has Jupiter in it. While Jupiter was forming, it sucked up a lot of the gas and probably altered the timing of the formation of the solar system. But it was pretty efficient at also clearing out the solar system of comets and asteroids, with the exception of the asteroid belts, of course. But remember, Earth formed inside of the frost line, so Earth really should not have formed with much water at all. We think that most of Earth's water came from comet impacts, and comet impacts were probably much more common because Jupiter's gravity was changing their orbits and flung some of them towards the inner solar system. It's also possible that Jupiter's presence had a role in causing the giant impacts that formed our moon. And many people think that the moon would have helped life on Earth develop. The moon was closer to the Earth in the past, and so tides would have been much stronger in the past. And as the tide would come in, water could flow up into tidal pools, kind of creating a nice isolated place for interesting chemistry to happen. And before it was able to dry out too much, the tide would come again and put some new water into the pool. So maybe the moon was really important for life developing on Earth. And if we're going to be looking for aliens on extrasolar planets, we're going to be looking at roughly the size of Earth. So Earth is the largest terrestrial planet, which means that it's still geologically active and it has plenty of volcanoes, and that outgasses water vapor and air. We also have plate tectonics. We're the only planet we know of that has plate tectonics, and maybe that's because we're the biggest terrestrial planet. But if we didn't have plate tectonics, we wouldn't have a carbon cycle. And that means that Earth's temperature would have varied much more over the last 3 or 4 billion years, and life might not have been able to keep up with those changes, and it might have all died out. Because Earth has enough gravity, that also allows it to keep a hold of its atmosphere, makes it harder for the solar wind to strip it off or for the molecules to drift away to space. And because our core is still molten, and we have a decent amount of spin, we have a planetary magnetic field. And that protects our atmosphere from the solar wind, but it also protects life and our DNA from extra impacts from charged particles. And I've already mentioned this as we've gone through this list, is the carbon cycle, climate stability. We think that's a really, really, really important reason why life has been able to do so well on Earth. So there's no way that the astrometric method or the Doppler method would give us any information about possible life on planets. But while a planet is transiting, it's in front of its star. And while the starlight is coming through the planet's atmosphere, assuming it has an atmosphere, right, the atoms and molecules in the atmosphere would change the spectra. So using the transit method, we might be able to see some signs of life. Now here's a spectra of Venus in the infrared, and you can see that there's a little feature from sulfuric acid. And since Venus's atmosphere is mostly carbon dioxide, you have a very large noticeable feature here for CO2. Mars's atmosphere is also mostly CO2, so you can see that as well. So if we see carbon dioxide signatures in the planet's spectra, it's not really going to mean much. We think that carbon dioxide atmospheres are going to be very common out in the universe. But there are a couple of molecules in our atmosphere that are quite rare, we believe, and they're because life exists on Earth. So if we find a planet and we get a spectra of it, if it has this very specific absorption feature from ozone, we would get really, really excited. So the Drake equation is a way to imagine the number of civilizations with whom we could potentially communicate. And I always imagine this is applied to the Milky Way. Right, so we're going to break it down into a couple of different factors, and they all get multiplied together. Right, the first one, this represents the number of habitable planets in the galaxy. And we don't really know that, but we could take a guess. F life, the fraction of habitable planets with life. And we have no idea what that fraction is. It could be practically 0 or almost 1. F civ, the fraction of planets with life that eventually develop intelligent life. And we have no idea what that number is, but somewhere between 0 and 1. And then you've got F now. So this represents the fraction of communicating civilizations that are around now that we could communicate with. Because so far, we haven't really specified when we were looking. You know, some of these civilizations may have existed in the past and already died out. Some of them might exist in the future and they're not around yet. So when you imagine this fraction, you're going to kind of be imagining, how long do you think a civilization can exist for and communicate with radio waves before they die out? Are advanced species too complex to support for very long? Do advanced species wipe themselves out? Or do advanced species perpetuate for a very, very long time? So let's kind of imagine some values and play around with this a little bit. So, number of habitable planets, I picked 100 billion. It seems like planets are really, really common in the galaxy. We've just started finding them in the last 10 years and we already know of thousands of them. So, considering that there's 300 billion stars in the galaxy, this is about 1 habitable planet around every 3rd star. How about F life? The fraction of the habitable planets that eventually develop life. I am just imagining, how about 1 out of 100, right? So F life, the fraction of habitable planets that will eventually develop life. 1 out of 100. F civ, how about 1 out of 1,000? And F now, my guess right now is 1 out of 1,000. So the number of civilizations that we can likely communicate with is 1,000, but remember that's just a guess. Feel free to pick your own values here, kind of argue how likely you think all of these factors are, and see how many you come up with.